Alrighty then. Alright, hi guys, how's it going? I'm going to work through how we should parse through the data that we collected during the lab, and also kind of explain some concepts that we covered maybe in lecture during lab that maybe some people were still kind of held up on, and hopefully by the end of it, you'll be able to grasp a lot more with the lab. And be able to write your lab report a lot more effectively. On your Blackboard, there should be kind of like a sample report that I sketched up. To be quite honest, it's not going to be like, here's lab one, I did it for you, just basically look how I did it, now you do it. It's more of like, here's how I generally structure things, and I kind of looked at what Dr. Margaritas has in his outline. I kind of modeled it after that. But you'll see how I want things captured. I gave some hints on how to put like equations down, how to auto number things. There's a very easy, quick way to do it. So yeah. Also, I want to apologize. I wanted to get this out earlier, but unfortunately, I have been de-skunking the house with my very helpful fiance. And before people comment any suggestions, just know that while tomato juice is always on the option, we've also found some pretty good success with 1 quart hydrogen peroxide and a 1/4 cup of baking soda and some Dawn detergent, like a few tablespoons of that. So in case you unfortunately ever need to use that information, there you go. One quick thing, I wanted to show this demonstration, the difference between rotational and irrotational flow. So back around, I'm just going to throw out a number, like let's call it the 1600s, a bunch of the world's smartest people wanted to get together, and they had this sole purpose of making undergraduates suffer more than they already are. So they made horrible naming conventions just to confuse people. So let's go through the difference between rotational and irrotational flow. So rotational flow, you can kind of think of it as like, imagine being on a merry-go-round, right? So I quickly drew up these sketches. As you move around the merry-go-round, the further out you go, the faster your velocity. Typically scales linearly, but should scale linearly. And in lab, what you have is this parabolic shape that seems to spin. So imagine like a disc, but then you like carved out essentially this cup in the middle. And as you go out, you can see how the slope gets more and more horizontal, and that's essentially just because it's supposed to be getting faster and faster the further you go out. But let's see what that actually looks like. So you can think of it like a ship, right, going around this curve. The nose will always point in the same direction as it moves around the curve. Now, irrotational flow is the opposite, right? So the closer you get to the center, the faster it goes. It behaves as 1/r. So you can see right here. If you have a ship pointed, like let's say north, as it spins it around, you'll notice that it won't align with the direction of which you are traveling. They kind of move irrespective of each other. So things like tornadoes, or if you pull the drain to your sink, expect to see irrotational movement or irrotational flow, and this is what it looks like. Also, shout out to Sander Huisman. I guess that's his YouTube channel. So, thank you, guy. Anyways, all right, let's get to the data. So, I kind of already fleshed out your data. I just made mock data, so if you use all of this, I will know, because A, I just made it up all on the fly, and B, it's going to look pretty awful. So, let me hide some things real quick. You guys will have essentially something that looks like this, right? You'll have trial 1, and they'll say 1, 2, 3, 4, 5, 6. You'll have your number of revolutions, your time. Then your frequency, you'll notice this hertz. It'll be in revolutions per second. You'll have your respective radii, then your measured needle length, your height from datum, and then, let me unhide this, you will have a column that will be theoretical height, right? Now, there were some people that were questioning, what do I put here? What's height from the datum? Why do I need to choose specifically my Z0? Because if you guys remember in the original equation, let me pull that up real quick. It was equation 9 here you go. So no one has an issue with this. The issue comes with this Z naught, right? So it's the elevation of the lowest point of the vortex at the center. So what do you put there? Well, I chose two things. So if you chose Z naught as 0, your theoretical height then is just this term, right? It's just your speeds. But if you follow how equation number 9 has it, this Z naught is whatever the lowest evolution is. So this is basically the pin that's at the center. You can think of this as the bottom of the vertex, right? So in this bluish gray column, you can see here that I start Z naught at 0, and then in the white column, I have it as Z naught is equal to L6, or this measured needle length, okay? You also have a column that says height from datum. I saw some people confused on that. What it basically means is that you are going to take whatever your needle lengths are, and then you're going to subtract the height of your vertex. So in effect, you can see here, I have this entire column subtracted by this base value. So why do you do that? Well, that's a great question. So this is one of the reasons, I don't know where it just went, but this is one of the reasons why you would use height from the datum versus just your measured needle length. So there's supposed to be a curve that forms right here, but essentially you have so the smooth line represents your theoretical curve. The points, your experimental data points, are just left by points, and you have this nice curve that goes underneath. So, you can either have it starting from here, so every graph will be unique since they all start from a given Z naught, or you start it from the origin. So down here, this is your height from datums. Here's your measured needle length. Now, for what we ask you in the lab manual, so let's go down here. Doesn't really look like we ask you to plot. I don't see anything. We don't ask you to plot from the datum, but let's say we are interested in that. Why would you be interested in that? Well, I'm going to plot, you can see here's trial 1 and trial 2. I'm going to plot the theoretical heights from Z naught is equal to 0. And/or I'm just going to do height from the datums, right? So if I do height from datums, you plot them together, you can now see a better relationship for, okay, what happens when I just vary the speed. So now I don't have to worry about, let's say this was trial 1, this was trial 2 for whatever reason starts at a very slower rate. Now I can't really make a great comparison with each other, right? But when I compare it from the datum, where I kind of like zero it out, so they essentially quote unquote start from the same spot, now I can specifically measure quantities that will affect the height, such as the rotational speed, right? So that's why you would use it or calculate it from height from datum. Okay. So that was extremely long-winded. Let me show you how you are going to parse this out. So already, make sure you have your data table uploaded into Excel. But here's the problem, right? You see here that, where is it? Your equation has you do r squared, omega squared. Omega squared is your angular frequency. Angular frequency has units radians per second, right? So if you look here, this is F. Okay, well, that's revolutions per second. That's not the same thing. So what you're going to have to do is create another column in between. We'll call it angular frequency. So all you do is just multiply this column. You can see here, it's just multiplied by 2 pi. If you want to be really technical, you do 2 pi radians per 1 revolution, and that's how you get your appropriate values, right? Cool. So now that we have our omega and we have our radius, that's how you get these values. So just for simplicity's sake, I'm just going to create a graph. I should be telling you to use scatter with straight lines. For now, I'm just going to use smooth line markers because it doesn't matter for this lab. But the reason why I'm going to use smooth line markers is because I want to denotate or demarcate between my theoretical equation and my experimental data. Alright, so let me just make a blank one. I usually like using the blank ones because then you don't have to mess with the data that's put in erroneously. So we select our data, we're going to add a series. For now, you don't have to name it anything because we actually want 3 different equations. So for my x value, we said, sorry, I lied to you. We can actually do experimental data. So we want to plot r versus z. So let's do radius. Then we're going to have our measured needle length. Okay. Cool. And then let's put in our theoretical. I really hope I spelled that right. But I am an engineering person, not a speller. So I use measured needle length. So I'm going to have to use Z0 is equal to L6 to make sure they light up appropriately. And hey, look at that. You can auto format quick layout here. And then we could change this to distance. Let's do radial distance from center. And that's in meters. And then this one is height, height of free surface. If I really want to be technical, I could put like from bottom of container or something like that, but it is what it is. And then trial 1. Okay, so this is what's going to make you look a lot more slick when you turn in your data, or your lab reports rather. So double click on just any feature of this graph. And now we are going to click and select this theoretical curve, right? If you go to the paint bucket, we'll go to markers, marker options. You click none, right? Because we just want a nice smooth curve. Then let's go to our blue curve. So this will be our data that we collected. You should not have lines on this one. So we're going to do no lines. So now what we have is our expected theoretical curve and then our data points pockmarked around it. So we can do a visual analysis, quick visual analysis, and say, hey, that looks pretty good. We don't have like this annoying lined connect the dots of our experimental data because that just obfuscates, makes things a lot more cluttered. So now if we look back at the lab manual, things that I asked for. So cool. We made a column for question number 1. Number 2, it asks you draw V or Z versus R from experimental and theory. Draw one figure for each trial. Comment or agree. Comment on an agreement or disagreement between experiment and theory. Blah blah blah. Okay, cool. So what I don't want you to do is just drop these off in your lab report and then just never talk about them. You should never, ever, ever, ever have any dangling graphs, right? You always want to introduce them, say, you know, like figure 2 is the experimental versus theoretical data for trial 1, right? You can see here from this graph, it looks like there's pretty good agreement going across the curve. We could see some, if you really want to, maybe you could figure out the maximum percent error or percent difference, relative absolute error, but I want you to basically talk about it. You can't just show me a graph and then just go away and it just exists in the ether now. That's not helpful. So be sure to discuss it in your lab reports. So you'll do this for trial 1, you'll do this for trial 2, trial 3. I don't see anything on here that states, hey, you need to put these all on the same one. So in other words, like, have a graph like this. I didn't see that there. If you do keep this on here, though, first off, it'll impress me, make me happy, show that you're thinking about things. I feel like I should reward people for, really thinking about their data and what that means. So, I don't think I'm going to give you like more than your maximum grade on that lab report. But I feel like it, if I see that, maybe I can compensate for lost points elsewhere or something like that. I just want to see that you're thinking through this, right? But yeah, so, another thing, trial 3. Trial 3 is the spillover trial, right? So it shouldn't line up your experimental data shouldn't line up very well with your theoretical. I've had some people, even with the presence of it spilling over, for some reason matched up pretty well with experimental. Life is mysterious, but ideally, 3 shouldn't look as good as trials 1 and 2, right? Because you don't have steady state, you have a lot of backflow, you have literally mass leaving the free surface. So don't feel too overwhelmed if 3 doesn't look that great as 1 and 2. However, if 3 is better than 1 and 2, it could be that you didn't wait long enough to reach steady state. But again, that's not too bad. I just want you to be sure that you talk about it and address it in your lab reports. Please, I am begging you, never say, oh, it's just experimental error. That won't work. You must be more specific, like, we didn't wait long enough for steady state to be reached. Could be that, there wasn't a balance between inflow and outflow. I want you to think about it, right? Okay, what else? Is this observation for solid body rotation representing well the fluid motion? That can be rewritten. But yeah, so force vortex, basically, how well does it match up with equation 9? And just again, I want you to think about this. What does it mean to be a solid body rotation, right? For the same value of omega in the same system, do you expect different free surface profiles for different liquids? Explain your answer. So, let's think through this, right? Let's look at equation number 9. You have radius. We're going to assume omega is the constant, or is constant between these different fluids. And gravity should not change. I would be very concerned if it did. If you're still in the same place on Earth, and Z naught, Z naught. So with these parameters, looking at different fluids, what kind of fluid parameters exist among things like, say, honey and water? You have rho, density. You have mu, viscosity. The question is, does that play a part here? And I want you to think about that. If you need help, of course, reach out to me, but just think about it, right? And then lastly, consider a fluid, basically this system, so no water should escape, right? If you want to do this correctly. They give you a rotational speed, right? This is in RPMs. You must convert. Radius is in centimeters. Make sure you convert with consistent units. Would this be a good way to figure out what H is, right? Could you do this experiment? Let's say in a lab, right? In our lab. Basically, what I want you to do is figure out how tall H is. Right? How practical do you think this technique would be if all you had to use was the lab space? So, anyways, that about does it. As you can see, my laptop is starting to die on battery because I am a responsible person that charges it regularly. But again, if you have any questions, comments, concerns, personal philosophies, you can leave them down in the comment section below or personally reach out to me via email. I'll try having office hours posted the moment I upload this or upload the link to Blackboard. And if you have made it this far, I'm very curious. Let me know if you ever heard of a guy named Ray William Johnson, and the fact that he goes, check out my, or leave a comment down below. I want to see if there's a zeitgeist that's happening that we're now separating from. Anyways, that's enough of me rambling. Let me know if you have any questions, and I will see you guys later. Goodbye.